First, let's review a little bit. In our last lesson, we learned that distance isn't a specific term. We might use distance to describe the total distance someone travels. In this example, Jill walks half a kilometer to the east, half a kilometer to the west, a kilometer to the east again, and then finally 1.75 kilometers to the west. We don't know why Jill keeps wandering back and forth. As physicists, we don't really care. At any rate, Jill has traveled a total distance of 3.75 kilometers, but her displacement only looks at her initial position and her final position. Overall, Jill has traveled 0.75 kilometers west of her home. Distance is only a magnitude, 3.75 kilometers, but displacement has a magnitude and direction. We'll talk more about the difference in another lesson when we define scalar quantities versus vector quantities. And we'll also learn how to manipulate them. In the last lesson, we also distinguished between average velocity and instantaneous velocity. Here, we see Jill's same trip, but it's graphed as position versus time. Now that we have information about the time it takes Jill to travel, we can determine the velocity she was traveling, or more accurately, velocities. So we're going to break down Jill's trip into 4 segments. Because the line on the graph is linear, we know Jill is moving at a constant velocity. In the first segment of her trip, we can calculate her velocity as 0.5 kilometers per 10 minutes. The velocity is changing for each segment. Notice here that the displacement is negative. This is when she's walking west as opposed to east. The negative and positive velocities indicate direction of travel. In the third part of her journey, she began to walk a little faster. You can tell because the slope of the line is slightly steeper. The steeper a line on a position time graph, the faster the speed. So far in this example, I've actually calculated 4 different average velocities. I've taken a displacement divided by a time. These are essentially equivalent to the instantaneous velocity Jill's traveling at any point because her velocity is constant for each part of the journey. Today, we're going to look at motion with acceleration. In other words, when objects are speeding up or slowing down. That means that we won't have straight lines anymore. Of course, in physics, we prefer to use standardized units like seconds instead of minutes and meters instead of kilometers. We learned that last lesson. However, in the context of this problem, kilometers per hour makes more sense to me. I changed the minutes here to hours by multiplying by the conversion rate. And physicists do prefer unit rates, so we like to divide out our fractions. We can say that Jill was traveling at a rate of -3 kilometers for every hour, but just for that second part of the trip. Again, the negative sign is indicating position, in this case, west. So again, this is just for the second part of the trip. If we want to look at the journey as a whole, we can calculate an average velocity for the whole trip. My total displacement, or Jill's total displacement from initial to final positions, is -0.75 kilometers. It takes her a total of 58 minutes. And we're going to use the average velocity formula and plug in our -0.75 kilometers in 58 minutes. Do our conversion factor. And we will get that her average velocity over the entire trip, all 4 segments, was about -0.78 kilometers per hour. And I did round my answer here. the exact answer with um, all those extra numbers isn't as important to us. We're not going to talk about significant digits that much in this class, though. So I rounded my answer. So negative 0.78 kilometers per hour.